Now let's say you have already designed two filters, and one filter has this impulse response, another filter has this impulse response, and you are connecting them in series. So let us say this is something our system. Now find the Laplace transform of the overall system. That's the question. Now because you are connecting them in series, what essentially happens to the overall system? The impulse response gets converted. This is the impulse response of the overall system. How do you find the Laplace transform of two signals that are convolved in the time domain? It is just the product of their individual Laplace transforms. So what is the Laplace transform of this term? It is 1 by s plus 2. We can directly write because we know that 1 by s plus a has an inverse Laplace transform of e power minus at u of t and the other way around. So from this we can safely say the Laplace transform of the system that we are looking for looks like but this is not complete yet because we have to define what is the ROC. Now what is the ROC for this system? Okay, so the ROC for s plus a, remember we said is the real part of s should be greater than minus a. So that's what we were talking about. So now this system has an ROC which is the real part of s which is greater than minus 1, and this is the case where the real part of s is greater than minus 2. Now what would be the ROC here? Now the ROC here is that the real part of s should be greater than minus 1 because it should be the intersection of these two. So that is the final ROC that we have. So the ROC of the transfer function of the overall system is given by this. Now if we want to plot the pole zero plot, how many zeros we have? We have no zeros. There are only two poles. And where are the poles? So the poles are basically at minus 2 and minus 1. So we have a pole at minus 1 and we have another pole at minus 2. All the poles are all on the left half side, which means the system is stable. Okay, the system is stable. We can say that only if the system is already causal, otherwise we cannot use the statement that we use now. Is the system causal? Of course it is causal because it is rational and the impulse responses are all right-sided. So we can say that ROC is the right of the rightmost pole, and that is exactly what we are observing here. The ROC is right of the rightmost pole. The system is causal, system is stable. So we can say all those things just by looking at the pole zero plot because it includes the origin. So this is stable, it is causal, and this is what the ROC is. Now is this a low pass filter or a high pass filter? That also we can say because here the poles are all here on the real axis, which means the transfer function of the system will have a high magnitude when we are operating in this frequency range because they are closer to the poles. As we move away from the poles, what happens? The magnitude of this term increase and hence the magnitude of the transfer function will decrease. So this behaves like a low pass filter. So we could tell so much about the system just by knowing these two transfer functions. All right. Okay. Now this is an interesting problem where we have been given an x of t which is said to be even. Now given this property, study about its Laplace transform and the pole zero plot. Now let's see what happens to the Laplace transforms. How do you compute the Laplace transform? You just compute the Laplace transform like this: x of t e power minus st dt. Now if the signal is even, then we can just simply replace this with minus t and still this is true. Okay, because this is true, now we can simplify this and try to get some property on the Laplace transform side. So let us say we'll replace v equals minus t. If we do that, then the limits change. then we have x of v e power s v, and dv there will be a minus which will change the limits back. Okay. So, what is this quantity? Basically this quantity is nothing but, you can say, minus of minus s. So, this is nothing but x of minus s, or capital X of minus s. So, in other words, what we now see is that the Laplace transform is also even. The Laplace transform of an even time domain signal is also even. Okay. So, this is at least some property that we have due to symmetry. Unlike in the Fourier transform case, we had a lot of properties due to symmetry, but Laplace transform does not have such similar properties. But we see that at least for the even case, it inherits these properties from Fourier transform. Now, what happens to the pole zero plots? Now, let us say x of s was rational. If x of s was rational, then you can write it in terms of some zeros here and some poles here. Okay. So, then we have some poles and some zeros which are defined by ai. Now, let us say that this is equal to x of minus s. What does this mean? This means that this polynomial that we have written is also true. In other words, now here the poles and zeros were simply ai's and bi's, right? But here the poles are now minus ai's and minus bi's, but it's the same expression. So, the x of s is supposed to be x of minus s, which means these two fractions are exactly the same, which means these two sets also should be exactly the same. In other words, if the time domain signal is even, then for every pole, the negative of that pole is also existent, and every zero, the negative of that zero is also existing in the pole zero plot. So, if we have a pole like this, let us say this is a pole, then the negative of that will also exist. If we have a pole here, then the negative of that will also exist. So, if we have a pole here, then the negative of that will also exist. And if we had a pole here, then the negative of that also will exist. Right. So, similarly for 0. So, there is a reflection or symmetry about the origin that you can see for every pole and 0 that is present if x of t is even, and for 0 as well. So, this is a nice property that we can observe for the case of even signals. Now, let us solve this differential equation using Laplace transform. Now, this is the differential equation, so there could be a corresponding circuit which actually models this differential equation. So, how do we solve this? Even though this looks so big, actually we will see that Laplace transform helps us to solve this in a very simple manner. Apply Laplace transform here. What would you get? X of s times 3 plus this first order derivative, that gives you s, and on the right hand side applying Laplace transform you get third order derivative here, that gives s cube plus second order derivative s square plus first order derivative s plus 8. Okay. Now, the transfer function is h of s equals 3 plus s divided by s cube plus 6 s square plus 12s plus 8. This is nothing but s plus 2 the whole cube. So, we have already the transfer function in place now. So, from this we can find the pole 0 plot. So, the pole 0 plot. So, how many zeros we have? We have only one 0, and that is at minus 3. So, at minus 3 we have a 0, and at minus 2 we have 3 poles. So, 1, 2 and 3. So, let us say, so we have 3 poles at this location. So, this is how the pole 0 plot looks like. Now, this is once again a differential equation system. So if you solve this using partial fractions, you will get that everything will be in terms of e power minus at u of t, which makes this a right-sided signal in time, which means this is causal. So the ROC here is the right of the rightmost pole. So this is the ROC. So we have the ROC, we have the pole 0 plot, and we can also immediately say, look at this and then say that this is a low pass filter, because we have only 1 0 but 3 poles here. So any frequency values that are here close by will have very high magnitude, and as you move away the magnitude will fall down, and hence this is a low pass filter. Alright, let's try and find the impulse response. We need to break that into partial fractions. So how do we do that? So in this case this is quite simple, because we can write this as s plus 2 plus 1. The numerator could be broken down like this. So if we can do that, then life is slightly simpler. So this is a trick that we can do for at least this particular case. So we can cancel that out. Now all we have to do is find the inverse Laplace transform of these two fractions. So what is the inverse Laplace transform? So all we have to do is remember that formula that we already had, that 1 by s plus a power n will have an inverse Laplace transform of t power n minus 1 e power minus at u of t divided by n minus 1 factorial. So use that here. For the square we have t power minus 2t u of t plus t square e power minus 2t u of t divided by 2. So this is the impulse response. Clearly this is right-sided, and now let's try to find out the final value of the output when there is a unit step input. In other words, what we want to find out is y of s equals h of s times u of s. Why is that? Because our input x of t is now u of t, and we want to find out the corresponding output, which is u of t convolved with h of t. Applying Laplace transform, you get this. What is h of s? We know that h of s is simply s plus 3 by s plus 2 the whole cube. And what is u of s? The Laplace transform of the unit step function is just 1 by s. Now we want to find out the final value. So if you want to find out just the output in the time domain, all you have to do is just take the inverse Laplace transform of this expression here. Once again, you have to find the partial fractions expansion and then find out the inverse Laplace transform. Now if we simply want to find out the final value, we can use the final value theorem. So what is the final value theorem? The final value theorem simply states that x of infinity is just limit s tends to 0 s times x of s. So in this case we want to find out the final value of the output. So it's just s times y. So what is s times y here? So s and this s gets cancelled. So we have just limit s tends to 0 of s plus 3 by s plus 2 the whole square. So substituting 0 here, we get 3 by 8. So the output of this system eventually settles down at 3 by 8. What does this mean? So let's say this circuit, which is modeled by this differential equations, has a capacitor or an inductor or something. So the capacitor and the inductor's value will keep changing depending upon what your input is. Let's say your input is the step function. So remember, in a very simple RC circuit, the capacitance value was decaying, right, or it was increasing and it was reaching up to a particular point. So one of those cases might happen. So till what point would the voltage across the capacitor grow up to? If you want to find out that final value, eventually it will settle down to one value, right? So what is the final value? So if you want to find that out, a very simple tool is to use the final value theorem.